Yeah. Have you ever observed a black hole? You know what a black hole is? Uh, what you read in these videos and other videos about black holes, there's actually only one black hole that has been discovered, and that's at inside the center of our Milky Way. So they suggest that there's a black hole in all the universes, which I can agree with. But uh, what is a black hole? I've come up with in my research the idea that a black hole is the fabric of space without gravity. What is gravity? Gravity, according to Newton, is the interaction of planetary matter, galactic matter, at abundance, because there's trillions and trillions of galaxies, and that energy from the motion of these galaxies generate energy, which settles or interacts on top of this fabric of space. So what we see or think of as gravity in space is actually the difference between what we see through our telescopes and a black hole. What's a black hole? It's black. It's a fabric, the underlying fabric of anything that exists on it or in it. I prefer to refer in it because space is three-dimensional. So what we see when we look at a galaxy and all the stars around that galaxy are actually other galaxies. Inside the galaxies, like our Milky Way, when we look in the sky, we see all the stars that are generated in our Milky Way. We need a telescope to go further into the depth of the galaxies. I've read several books about space. A lot of them don't refer to modern time ideas or mechanics. Like I said, the discovery of a black hole is the one that is in our Milky Way. So we can assume, okay, that there's other black holes in the center of the other galaxies. I wrote a book. It's called "The Universe Without a Black Hole," uh, because our universe does not have a black hole. They may assume that it does, but it doesn't. Uh, that would be terrorizing, I think. I refer with the Erwin Hubble theory about our universe, which includes the expansion. Relativity does not include expansion. It does now in our videos, and like our Bible, it's upgraded to our new Pacific discoveries as they go by. But the original theory, there's nothing about black holes in it, unless somebody else wrote the book. And they would add that. And that's the way our theoretical physics go. I've written several books, including about 12 books about our universe. I've been doing research for like 15 years. But the idea that a black hole is black because it refers to not having any gravity. And what is gravity? Gravity is, there's two types of gravity. There's universal gravity, which is the dark matter we see in the sky of our Milky Way. the darkness between all the stars. When we look at the galaxies, it's the darkness around the galaxy, which is called interstellar space. Now, inside our galaxies, or inside, our galaxies are our planets, solar systems, etc. Whatever the Milky Way makes up as stars are what is in our Milky Way galaxy. Our planets have a gravity. Like I said, universal gravity is an empty vacuum. It sits outside the planets, which allows our planets and solar systems to be independent and have motion. So the activity we see in our solar system is everything is moving. In a subtle universe, that doesn't happen. So we have inside our planets, we have a specific scale of gravity. On Earth, it's 9.8 meters a second energy or force that we imply is gravity. And that was illustrated by Isaac Newton back in 1767. Space gravity was referred to as is the only another loophole that, besides Isaac Newton's idea, what he calls universal gravity, which is 0-point energy. There's no energy there. Our planets and all planets have a specific energy environment, which we call gravity, and that's 9.8 meters a second of force relative to the motion. But going back, when we see a black hole, it's black because that is the fabric of our space. We prefer to look at it as flat space so we can observe each planet independent, but I believe that most of all that it's three-dimensional. We are inside it, not on top of it. If we were on top of it, all the planets and stars would be evenly portioned, like let's say the whole population of the Earth is on top of a flat planet, even though it's round. Our observations are flat, even on this round curvature planet, because it's so big. The universe is bigger. Space is even bigger than the universe because space is where everything intertwines. That's where it's at. But it's three-dimensional. So that fabric is blank. There's no energy interaction in it when we look at a black hole. They don't know. It's my belief, and in my book, I refer to believe that black hole was made as a pod of some sort that exploded. In other words, we have the Big Bang, and we have second stage little bangs with the same force and energy, because just because all the energy was once a singularity, you could divide it up into all these pods, let's say, and the energy doesn't change just because they're smaller. It's still, even though it's smaller, there's less of it. The energy is across the board the same. So these pods, even though they exist and they're similar, which keeps one pod away from the other one, the way that gravity works in space now. I mean, they all aren't all bunched up together. They have a distance between them, which is constant. So when we look into a black hole, there's nothing there. It's a black fabric. That's emptiness. That's more of a vacuum, possibly a reverse vacuum, which space resists matter. Why? Because matter is energy in the content. E equals mc squared. As such, they are similar and create a atmosphere inside a vacant, empty vacuum of space. But a black hole, I think, is reverse vacuum. It has to do with itself. It's the same vacuum as an empty vacuum, but it has no energy in it. And like I said in my book, these pods are little bangs. They created what created the galaxies as we know it. The Milky Way is one. So all that energy came out of a pod that was pods that were created from the Big Bang. That's the convenience of observing a black hole, is that it is empty of energy. Other than that, I don't know. We call magnetic pull, which is not gravity, but it's a form of gravity that the black hole is sucking in everything around it. But I've never seen a black hole gobble up anything, except they say energy. So it's all theoretical, and this idea is that a black hole is black because it's the inside fabric of the space that we live inside, but outside of a black hole. So it's like the cosmic background of gravity and space itself. Without the energy for resistance and light from the suns to see everything, or a telescope to observe everything because it's lit up by the sun, the light of the suns, it's the same thing. It bestows the energy from the galactic point and the intergalactic point, which is the planets and stars that exist within our Milky Way and all the other planets that exist in all the other galaxies. And for that reason, all the galaxies are somewhat different. The elements are different. The observation of the environment of the planets that exist there are different. And our planet, Earth, retains life. And it's that viewpoint that makes scientists believe that there's life in other planets, on other stars and planets, other galaxies. We have to travel to a galaxy. For us to travel in a galaxy, we have to resolve the speed of light theory. The idea that we cannot travel faster than light. In my books, in my latest books, I illustrate a standard faster than light speed space travel anomaly or possibility. Now, unlike Einstein bending space, how can you spin a vacuum of nothingness? I mean, I don't understand it. The speed of light is constant, but if we did go the speed of light, we go in the past or the future. I don't see how that he toppled that. There is a force greater than light that exists, and the reason the speed of light is believed to be the fastest known thing, because light is the fastest observation of a proton particles, which made up particles that have no resistance. They travel at a standard rate and it doesn't change. To go more in that, you have to probably read some of my books. This observation hasn't been made by anybody that I know. Of course, like I said, I refer to the Hubble universe expansion theory, and I do have a new book, EVG, which is expanse vacuum gravitation. And it explains probably what I've explained in this video about our universe and the existence of gravity. I hope you like my videos. I hope you like my video. The topic is science, theoretical physics. It's theoretical because we have no real proof. But expansion is a force that is greater than light. Erwin Hubble said that, and I'm saying that now. So if there's a force that exists that is greater than the speed of light, which is equal v squared, or equals mv squared, relative to E equals mc squared, E would be 2E equals mc squared. The E, 2E would be twice as much energy as relativity predicts. You got to figure if the universe is pushing out, or space is pushing out, energy that is separating the keeping the galaxies separated in the universe. Well, it has to be a greater force than the speed of light. And like I said, I come up with a new book, EVG, expanse vacuum gravitation. Thank you.
Hey there, science enthusiasts! Ready to challenge everything you thought you knew about the universe? Buckle up, because today, we're diving deep into the mysteries of gravitation and energy. You've probably heard that the speed of light is the ultimate speed limit in the universe. But what if I told you that this might not be entirely true? That's right, the idea that nothing can travel faster than light is based on our understanding of matter, planetary and galactic matter to be precise. However, there's a twist. Matter as we know it has very little to do with the universe's spatial environment. Let me explain. According to Rodney Kowecki, the universe is actually capable of much higher speeds and energies than we've been led to believe. Think of matter as passengers on a cosmic train. The train itself, representing space, can move at unimaginable speeds and generate colossal amounts of energy. The more matter, or passengers there are, the more energy the train produces. So, while matter is bound by the speed of light, the space it inhabits is not. This means that the laws of relativity, which assert a universal speed limit, might not apply to the fabric of space itself. Mind-blowing, right? It's not just about how fast objects can move, but how space itself can expand and contract at different rates, potentially exceeding the speed of light. Imagine the universe as a giant, ever-expanding balloon. The surface of the balloon represents space. As it inflates, points on the surface move apart faster than the speed of light relative to each other. This doesn't violate any physical laws because it's the space expanding, not the objects traveling through it. So, if we consider Kowecki's perspective, it opens up a whole new realm of possibilities for our understanding of the cosmos. This could revolutionize our approach to space travel, energy generation, and even our comprehension of the universe's true nature. Isn't it exciting to think that there's so much more to discover? The universe is vast, mysterious, and full of surprises. So, stay curious, keep questioning, and never stop exploring. If you enjoyed this cosmic journey, don't forget to like, subscribe, and hit that notification bell for more mind-bending science content. Until next time, keep reaching for the stars. Hey there, space enthusiasts! Today, we're diving into the cosmic swell that's shaping our universe. Imagine a concentrated point at the very center of space, swelling and expanding at an incredible constant rate. This phenomenon is what we call the expanding universe. Now picture Earth's oceans with their powerful sea swells. They're influenced by our planet's magnetic core, creating those mesmerizing waves. The universe operates in a similar way, but on a mind-boggling scale. The cosmic swell isn't just a poetic term, it's the force driving galaxies apart, making space itself stretch and grow. And here's the kicker, this expansion is happening uniformly. Like ripples in a pond, except these ripples are galaxies zooming away from each other. So what's causing this expansion? Dark energy, the mysterious force that makes up about 68% of the universe, is the key player here. It's like adding more and more air into a balloon, causing it to expand endlessly. This cosmic dance started over 13.8 billion years ago with the Big Bang. Since then, the universe hasn't stopped growing. Each moment, it becomes a bit bigger, revealing more mysteries and wonders. So next time you gaze at the night sky, remember, you're looking at a universe that's continuously expanding. Who knows what incredible discoveries lie ahead as we keep exploring the cosmic swell. Stay curious, my friend. Hey there, science enthusiasts! Ready to challenge everything you thought you knew about the universe? Buckle up, because today, we're diving deep into the mysteries of gravitation and energy. You've probably heard that the speed of light is the ultimate speed limit in the universe. But what if I told you that this might not be entirely true? That's right, the idea that nothing can travel faster than light is based on our understanding of matter, planetary and galactic matter to be precise. However, there's a twist. Matter as we know it has very little to do with the universe's spatial environment. Let me explain. According to Rodney Kowecki, the universe is actually capable of much higher speeds and energies than we've been led to believe. Think of matter as passengers on a cosmic train. The train itself, representing space, can move at unimaginable speeds and generate colossal amounts of energy. The more matter, or passengers there are, the more energy the train produces. So, while matter is bound by the speed of light, the space it inhabits is not. This means that the laws of relativity, which assert a universal speed limit, might not apply to the fabric of space itself. Mind-blowing, right? It's not just about how fast objects can move, but how space itself can expand and contract at different rates, potentially exceeding the speed of light. Imagine the universe as a giant, ever-expanding balloon. The surface of the balloon represents space. As it inflates, points on the surface move apart faster than the speed of light relative to each other. This doesn't violate any physical laws because it's the space expanding, not the objects traveling through it. So, if we consider Kowecki's perspective, it opens up a whole new realm of possibilities for our understanding of the cosmos. This could revolutionize our approach to space travel, energy generation, and even our comprehension of the universe's true nature. Isn't it exciting to think that there's so much more to discover? The universe is vast, mysterious, and full of surprises. So, stay curious, keep questioning, and never stop exploring. If you enjoyed this cosmic journey, don't forget to like, subscribe, and hit that notification bell for more mind-bending science content. Until next time, keep reaching for the stars.
Oh, my name is Rod Kowecki. Why is the speed of light constant? Einstein said. Why is the speed of light constant? Because Einstein said.
I'm sure you've heard the news. Faster than light travel could be within our reach. Let's break down how this could be possible. Picture this. Space itself is stretching like a rubber band. In this scenario, there's a special point called zero-point vacuum density, where energy behaves differently. Imagine the vacuum density as a supercharged energy field. Now, if this density becomes greater than the light constant density, the energy limit set by the speed of light, things get wild. Here's the kicker. Under these conditions, energies might travel faster than light. Think of it like a speedboat on water. Normally, the boat has a speed limit because of water resistance. But in this new model, it's like the water suddenly offers no resistance, letting the boat zoom ahead unrestricted. So could we one day zip through space faster than light? thanks to these zero-point energies? It's not just a wild theory, it's a tantalizing glimpse into the future of physics. The cosmos might be more flexible than we ever imagined. Stay curious, stay excited, and keep it